ನಾಲ್ಕು ಜನನೂ ಕವರ್ ಆಗ್ತಾರೆ ಅಂತ. Did you switch now?
It's not. This is not.
Yeah, I think yes.
Yeah, turns on.
The light is on.
Oh, it's coming on now.
The microphone on that is towards the light, so keep
I
that
see.
towards your
Okay,
mouth.
yeah.
Yeah.
You close it over here.
Here you go.
Okay, so this is homework 3, wing constructions. So it's truss, monocoque, and semi-monocoque wing constructions. So the first one is truss data or truss wing data. There's 3 different types of planes that I chose for the data here. The first one was Wright brother planes, so I used the 1900 glider and then the 1903 flyer. So those are 2 planes, basically 2 of the first planes, right? And then I used 2 World War II planes. And then something that came up a lot when I was searching was this new concept plane that Boeing is currently building with NASA. That is a truss winged plane that would be more eco-friendly because of its construction. I thought that was really cool, so I also added that data. One thing to mention is that these 4 planes here all have fabric construction for the skin thickness. So the skin thickness is going to be a little bit different compared to metal constructions versus this, which is a concept plane, but it would be metal, right? It would be aluminum. So
are there no composites in that? It's full metal?
no, I think there are composites, but you know, it would be metallic in nature compared to the fabric wings. So yeah.
You had certain things at the bottom.
Yeah, I mean,
You covered them all?
Go over that.
Sure.
So basically, one of the main points is, as he mentioned, is that these fabric furniture skin, mainly for the right flyers, flyers and different aircraft, these fabric, just because it was cheap, light, and it was easily accessible, it's something that they had available at the time. And the whole point of using a truss structure for the Wright brothers, at least, and also for some of the other ones, is that the wings themselves can be easily modified. So for the Wright brothers, they can easily adjust the wing geometry to test out different variations. And in the new, actually, the new Boeing, the concept has folding wings, so that when it's in storage, the wings themselves can actually fold in. So the truss design helps them to easily manipulate it, as opposed to semi-monocoque, where all the internal stuff are hard to modify. So.
Yeah, so now we're going to talk about monocoque. So we really struggled to find a lot of monocoque structures. I tried to ask ChatGPT in several different ways. It tried to provide some answers with all of them still being semi-monocoque.
Right.
Because also just purely monocoque structure, if it's used, is mainly only for the fuselage, because it can be uniform, so it doesn't need extra load distribution sometimes. So the first 5 aircraft initially thought to be monocoque were found out to be semi-monocoque. We decided to still include them to just supplement the data of the graphs. And yeah, the reason why there are not many completely monocoque wing structures, because simply monocoque tends to fail in buckling, and on the wing there are too uneven of a load, so it's really hard to just make a really thick skin for it to work. And yeah, and the only designs that attempted purely monocoque were in Pioneer Air 1903 to 1914. And then another interesting discovery that ChatGPT provided is geodetic, which is somewhat similar to monocoque in a way that main loading members are basically skin and follow airfoil shape rather than spars necessarily. So can you go next slide? which is basically the geodetic aircraft. So it basically has,
Is the last one that you're talking about? The one in the last column? Yeah.
Yeah.
This one?
Yeah, like
What you had in
last
the last
two
column.
aircraft
Okay.
in the previous slide. So originally used for airships because it's just an outside structure, so it
Yeah.
maximizes the space inside for whatever gas is used to lift the plane. So yeah, instead of ribs and spars, diagonal braces, which the torsional loads cancel out because of the design. And the main loading members are right next to the skin and they're uniformly placed, for the reasons of torsional load cancelling as well. And so all of the planes that had this structure, they had a linen skin, but which basically didn't provide much of a structural benefit, but rather just for aerodynamics, while the main structure was inside. So I kind of thought it's interesting in a way that you can consider the inner structure as skin, since it foils the airfoil shape, and it doesn't have that many members, and so that's why also these two aircraft become the outliers, because I took the thickness of the beams used for the outside structure as the skin thickness, which came out to 2 inches, which is a lot bigger than the rest. But since it is a main load-bearing structure, it makes sense. And this is basically how the structure looked on the inside of a geodetic plane. And majority of them, because these were used on World War II planes, and the planes basically came out without skin, just the carcass left, but it was a really sturdy structure. So it could stay afloat, even like looking like this.
So it's good you took up the most challenging portion, which is this monocoque. And I'm glad you brought up the airships, because there's a lot of renewed interest in airships today, especially for high altitude applications, what are known as stratospheric airships. So this is like a poor man's satellite, or a geosynchronous satellite you typically have at 36,000 kilometers altitude. So the launch costs are much more. So whereas if it's in the stratosphere, which is just a few kilometers above the Earth's surface, it gives you much higher resolution pictures because it's much closer if you have the same kind of photography equipment. So there's a lot of interest world around. US, France, UK, India, and Japan are all China are all working towards the stratospheric airships. Since this particular course is generally titled as structural analysis rather than aircraft structural analysis, which a few courses around the world, some of the universities call it that way. But since it's an aerospace engineering course, feel free in the future also, if you can't find any aircraft examples for some homework, to look at alternates, like airships is one example. So there are many others as well. And also the reason why it's so challenging to find that is, see, whatever we do as engineers, we want to do something better than what we ourselves can do at the human body level. The only reason why we invent certain things is we are able to do it, but we are able to do it much more at lesser speed or lesser distances or whatever. So, but we want an engineering structure to do something better than that, faster than that, or more economical than that. So that's the direction in which we want, and the direction in which the aerospace structures or aerospace vehicles have moved is to move faster and longer distance and carry more payloads. And once you have that, it's impossible to have the monocoque construction, because as Ivan pointed out, it buckles. If you want to avoid that, you increase the thickness, the weight goes for a toss, and it can't even take off, so it becomes so heavy. So that's the whole idea behind that particular challenge. So, but it's important that we study this at least historically, and also futuristic things like stratospheric airships, because it kind of becomes like the borderline between your truss, what you already presented, and what you're going to present next, which is the semi-monocoque construction. So it came as an intermediate, and if the monocoque was not there, probably would have never thought about the semi-monocoque. For lack of that, I would accept this, but I would rather say these are all typically if the let's say the linen is not taking any load or it's not helping, then this would be more like a truss-like structure rather than a monocoque construction, right? Or if the linen were to be taking the load and more of the load than any of these supporting structures, then yes, it becomes more like a semi-monocoque construction rather than a monocoque. So I understand the difficulty in trying to find, and I'm glad you also pointed out that you tried to use ChatGPT and the answers were not appropriate because it understands some of the semi-monocoques as the monocoque construction. So these are some of the limitations of LLMs that we would like to see how we can probably go around. Probably future ones would do better, but the current state we'll have to do a lot of human intervention.
It's not even necessarily ChatGPT, but a lot
Right.
of websites
Okay.
also
Oh, really?
use, like, they just
Okay.
write monocoque
Okay.
while it's semi-monocoque.
I
So
see.
you
I
actually
see.
always have to find a wing cutout to
Right,
actually
right.
see the spars
Uh-huh,
and ribs inside.
uh-huh.
And only then you can understand that it's actually semi-monocoque.
Okay,
It's purely.
okay. Right.
Yeah, all the
That's-
websites just said
Okay.
That's what's really interesting is like we double check it to compare.
Uh-huh.
It's like we'd say, oh, it says monocoque, let's see what like the internet says,
Uh-huh.
and then we go look and it's like the first ever fully monocoque plane. But then like Ivan said, he would actually took the initiative to like look at images of the wing
Mhm.
and saying if you look at like the 2D plan forms, that like
Mhm.
there's clearly
Mm.
like structures inside of it, so it's really not monocoque. Even though
Okay.
everywhere on the internet would say these planes are
Right,
monocoque,
right.
so it's really weird like why,
True,
like
true.
who came up with
Right.
this and why they're saying
Right,
that. But,
right.
um,
And since LLMs are sourcing information from those
Yeah,
and eventually
yeah.
building it up, obviously they would go even more erroneous.
And like you had said too, 'cause like when I researched too, a lot of what came from like the monocoque sources was stuff with boats, and so it
Mhm.
seemed like the original monocoque structures, and a lot of where like if you were to find some data for like skin thickness of monocoque structures, it was on boats.
Mhm.
So I thought that was kind of interesting that you mentioned like you could look at other vehicles too. So I think
Mhm.
boats,
Mhm.
or even there's some other maybe tanks or something that
Yeah,
were like this kind of
uh-huh.
monocoque design.
Mhm.
So
Mhm.
I thought that was kind of an interesting
Right, right,
fact
right,
too.
right. Yeah, because whether it's aerospace or any transportation, the main requirement is the same. You want to do
Mhm.
things at a lesser weight. It's just that it becomes that criteria becomes more and more stringent as you go for more and more higher performance from the road to the ocean to the skies. So that's the challenge levels is building up, and so the solution also has to be more and more innovative. I'm really happy you're bringing these points out, because more than what is the data and what is the eventual plot, I want this process to be more evident in how you're getting there. So it's that what are the sources of information, how you're trying to process that, and eventually present it in the way that we want it, right?
Yeah.
Go ahead.
So with the semi-monocoque aircraft, I thought it was really interesting how it doesn't matter like the use case of the aircraft, you see it across sectors. So from supersonic fighter jets to bomber planes to modern passenger aircraft, they're all using semi-monocoque structures, and so it really kind of showcases how it's a really beneficial design that works like across like speeds or weights or payloads, like whether or not you're carrying passengers or whether or not you're carrying cargo. And so it's clearly been in use for quite a while because of its benefits, and even today these most modern aircraft like the Dreamliner are still using that as its design. And like we've already mentioned, like some of the most futuristic aircraft are starting to look at that truss-based design as well. But even like we talked about, even with that truss-based design, it would probably still make use of like a combination like truss semi-monocoque design where you're not entirely going to just truss it by combining both and like getting the benefits of both in one. And so you can kind of see that, and we'll see this more in the plots that are come. But there's kind of quite a variety of skin thickness across the aircraft, and even like if you look at like certain types of aircraft, like even if you just look at passenger planes or just look at fighter aircraft, you'll see that there's quite a wide variety. It doesn't always seem to correspond to speed or to weight. It kind of just is quite a variety of data points. Part of it is maybe just because there isn't necessarily always a correlation. It can just kind of depend to design. So the main thing we'll see in one of the plots is the 787 is always an outlier, and we think that's probably just because it's so modern and so cutting edge in its design technologies, but also because even with the semi-monocoque design, it was still quite challenging to find skin thickness information. Like we had already talked to you about before, like a lot of the information just kind of came off like forums online and like engineers saying this is what it is. Kind of just having to go off like trusting them, and like even like you see in the forums, like people would say, yeah, that sounds right, I agree, but I can't say any more than that. So it's almost like a lot of this data is pretty proprietary to the company, and so finding really precise exact numbers can be pretty challenging. And so that might also correspond to how accurate these numbers are. Like if there's maybe like if it's close, but maybe there's slight variances between them. Like if you're looking at like 0.02 to 0.04, that's double, but that's still such a small relatively measurement that like if you were to go up to 0.03, like to the human eye, that would be nothing, but that would make a huge difference in the plots in terms of how close these data points were to each other.
And also, as you said, that variation 0.02 to 0.04, again, it would be very, very different in different components like the fuselage or the wing or the stabilizers. So we are only trying to get an order of magnitude understanding over here rather than going to the actual values, because it's always a range.
So as Ivan pointed out on his slide, where you see two outliers on the very right, those are the Vickers bombers that use the geodetic wing design, where we use the beam thickness as a skin thickness.
Those
That's
two
why
points
they're
on
always
the
on the right.
Okay.
You'll see that on every graph where the thickness is just so much significant than with other airplanes. But in comparison to that, I believe the top is the Boeing 787, which Matt also said is also going to be a big outlier on this, where it has a large wingspan because it is a larger plane. It's a passenger aircraft. It has that high aspect ratio to help improve flight performance. Other than that, you'll see that the other passenger airplanes are below that, using the same kind of logical reasoning, where they are larger planes, they have to carry a larger load, and so it needs a longer span. That's why we'll also see that the skin thickness for these planes are a lot smaller than more of the fighter planes, because the weight distribution, based on the fact that the span is so large for the wings, having a skin thickness that's bigger will just accumulate into larger and larger weight. So they'll use smaller skin thicknesses. Also, what we'll notice is that while there is like this inverse relationship, there's also this inverse relationship between skin thickness and like the year that the plane was made, because as we progress into the future, they use more and more composite materials. So for example, the 787 and the other passenger aircrafts use carbon reinforced polymer composites in the wing to help reduce the weight, and we'll see that later on. And in the bottom, you'll see fighter jets. They're smaller planes. They're carrying less of a load, mostly just the pilot and whatever weaponry they need along with that. So next slide. This is the maximum takeoff weight and the skin thickness. So on the top graph, we included the Boeing 787, but on the bottom graph, we took it away because it's such a big outlier, so we can see a better distribution of where the groups are. And again, you'll see on the right, the Vickers bombers obviously are very big outliers because of the skin thickness, but they are relatively around the other, like the maximum takeoff weight of the other fighter jets, where they're all like near the bottom. Other than that, we'll see that there always is like a middle dot right here that's the new concept design for the Boeing Sugar, and that's why it's always has a decent takeoff weight, because it's also considered like a passenger aircraft, so it takes up that big of a weight. And obviously, for takeoff weight, you want the fighter jets to be as low as possible so they can carry as much artillery or weapon as possible, and that's not necessarily including the plane weights.
So for the Sugar, first of all, that plane has not been built, right? It's just a concept plane, and the data keeps changing, right? So the data that I used for that was the Sugar 4, which is the 4th iteration of it, but it hasn't been built yet. So obviously, this data point will keep changing, and so scientists don't really know exactly what it would look like.
Can you just clarify what is the difference between the top and the bottom?
So this one has the outlier point, and this one doesn't. Yeah.
Okay.
Just so that you can see what the data actually
so
looks like without the outlier.
Okay.
Right?
Also, one interesting thing to note before you change the slide is that there's always two dots together near where there's like a significant skin thickness. And those are both of the Wright brothers planes where they have a single
Oh,
more
okay,
significant
okay,
things together.
okay. Uh-huh.
So it's like it kind of mirrors what the Vickers bombers is.
So
That's
on this
also
scale,
why-
they probably had comparable takeoff rates and.
yeah, that's why it's also really
Uh-huh,
low for the Wright brothers flyers.
Okay, okay.
And yeah, and if you consider Vickers bombers linen skin, I think they will fall around.
Mhm.
Yeah.
Mhm.
Last is the skin thickness for cruise
Right.
velocity.
Uh-huh.
So for our fastest airplane, which you see on the top, it's actually not a passenger airplane, but it's actually the F-100 Super Sabre fighter, because that's like a supersonic fighter jet. And that's why that's why the speed is so high. And the reason why the skin thickness is so low is because it uses a semi-monocoque design, so it doesn't need to have thick skin as much as the other planes do. Of course, we have the Vickers bombers on the right again. Followed by lower down is the cruise velocity, because passenger aircrafts generally travel at a fast speed, so they can provide for the customers as well. You'll notice at the bottom, the more like bottom left airplanes, this cluster over here, they have a lesser speed, mainly because and they have lower skin thickness because they're a monocoque design. Because it's a monocoque design, they can't go as fast because then they're encountering more stronger aerodynamic forces. And so if we go to the right, you'll notice that as we go to the right, it's more of like fighter jets. So they are going a little faster, but they also have some kind of support where it's like truss based with other ones.
Okay, okay. Yeah.
So like we kind of mentioned, I think there's better like relationship between like age of the aircraft and skin thickness versus some of these other metrics, just because like I said, as technology gets more and more advanced over time, there's new manufacturing techniques like composites that allow for thinner. And so I think cruise velocity is actually probably one of the best things we have to compare it to, since I think not entirely, since it does vary from type to type, but over time I think we generally get faster aircraft as time progresses, and so like you can kind of somewhat correlate cruise velocity to an age of the aircraft. And of course there are some outliers, like a supersonic fighter aircraft of course is going to kind of be a difference. So you can kind of see how this is true, where as you decrease in velocity, you get thicker and thicker skin thicknesses, and as you have like the really, really fast aircraft, they always have very, very thin. So I think that was like the closest correlation, where either A, because of like the advance in technology of the aircraft, or even just the use of like a supersonic aircraft, like I said, it's going to have a much thinner skin thickness versus some of these heavier, bulkier, kind of older aircraft. And so we thought that was kind of one of the biggest kind of correlators. Since that really seems to change the most over time. With the 787 Dreamliner, especially as being the newest aircraft we looked at, and that was always way, way out there because of how new the technology was that it was using in its design.
You can really see this because maybe like these two are, as we said before, are the Wright brothers different two planes, and as we go to the left, it goes to World War I and the World War II fighter planes. And so the progression of time and better technology allows us to lower the skin thickness as well as raise the speed. This is a good measurement of progression. And then next up, I think we have our various sources based on whichever wings we did. So this is the truss wing sources. Next up was the monocoque as well as the geodetic, two different geodetic wings. And lastly was the semi-monocoque structure.
If you just go to one of those pictures, the graphs that you had shown. So one of the ways in which you could probably, I mean, it's an excellent piece of work considering the limited sources of information that you have and try to put it together. But a few ways, suggestions for how it could be done probably a little better. This is something that's very commonly done with the experimental works when you're publishing data. He's an experimentalist, by the way. He's just substituting for Fanindra today, Prashant Kumar. So he's your TA today. And so typically the way we do for some of these is, as you said, there's not a single skin thickness for a particular aircraft. There's a range, right? You mentioned 0.02 to 0.04 inches for a particular aircraft, right? So you typically give a band for that. So you, instead of just a point, you just show an arrow and you show that range of skin thicknesses for that particular aircraft. The other thing is, purposely I gave this cruise velocity in a later class. I'm glad you could do that in spite of your Mysore holiday. But you should notice the difference between this particular thing, which is directly talking about a performance parameter, as opposed to the other two, which is talking about the gross takeoff weight and the wingspan. because those are indirect ways of talking about the performance. A direct way of talking about performance there also, if I wanted to give, instead of cruise velocity, I could have talked about the range of the aircraft, or the payload of the aircraft. Instead of the maximum takeoff weight, what is the payload weight that it can carry? So that's a direct implication of that. And another thing apart from that range that you can bring up, and probably in future homeworks or for any other courses as well, is also when you have clusters like these, or at so many points, it becomes a little difficult to decipher what is what. So since you have three categories here, which is the truss-like, monocoque and semi-monocoque, you could have three different colors for these dots.
I know.
So
I should try to do that.
Right,
It's very difficult with the programming, so I was just like, let's just explain it in like why.
Okay.
But it makes sense. Like,
right,
yeah.
because visually looking at it, and
absolutely.
it gives a much more.
Or we could have just
Yeah,
like
right,
circled
right,
it or something.
right, right. And because these are not like very rigorously scientific or mathematical equations on the basis of which these points are arrived at, because design is as much an art as it is a science, and so there's a lot of decision making involved, and just because a particular company has a certain design philosophy, they might go with a particular choice which may not be the same choice another company makes. So you might have, even if you have clusters, it may not be all of the same kind. So it's always good to have different colors. That way you know why is in a bag of oranges, why is an apple occurring? In orange colored ones, why is a red colored one or a green colored one appearing there? So that makes you think a little more aloud and see what could be the issue, and what are the specifics about the design, if information is available. Okay. You had any questions, Prashant? Okay.
I think
Yeah.
I was gonna like over like on top of the graph like make dots, because I couldn't like do it in the program itself.
I think-
so that was
Yeah,
like-
Google Slides
It's
just, I
just
feel like
so
doesn't
annoying.
have the dog
It's
shit.
so
I think
annoying.
if you wanted
What did you
to
use
power.
for the
we use
plot?
Excel, but if we wanted
Okay.
to do
Yeah,
like
you
No,
can-
we
different color
use
points,
Google Sheets, we didn't use Excel.
Yeah.
In Excel, actually, you
Yeah, you
wouldn't
can,
be able
yeah.
to.
Yeah, most
do the
software will
points.
give you legends and also the
I could've just
different.
done it by hand,
Yeah,
to be
right,
honest.
right,
Just like,
right.
this is the deal.
Okay,
This,
okay.
Just done. Which would have been given the same result, right? But,
Sure,
yeah.
sure, yeah. Right. So it's just a question of leveraging some of the tools that are available today to the best. Because see, if you have worked on it, it's very clear for you. But somebody
Right.
who,
No,
because
absolutely.
you spend few hours on it, and we spend just a few minutes on it, it becomes much easier for us to grasp the information if it is visually differentiated. All right, thanks. Anything else you had to say about this? Okay, good. So let's continue with the class.
Thank you.
Thank you. You can continue the same video. Yeah. The time ticker is going on, right?
Yes, sir.
Yeah. I'll just open this up. Still the marker pen, did you see somewhere?
Oh, here it is. Here we go.
Thanks. Yeah. So remember that we've been generally saying that this whole subject of structures, whether you're doing analysis or design, essentially involves the geometry and the material. And in the geometry, we talked about the shape and the size. And we also reasoned out that we need to have shells, which by themselves are monocoque, which is what you presented about. And you reinforce them with beams or 1D structures. to get to semi-monocoque, and the second category is what is of, or in your thing you're talking about a shell truss as well, so it's a third category that we are most interested in. So most of our focus will be on this, which means that a lot of our work will be related to 1D beams, right? But now we're done with that question of answering certain questions like why, what, where, and how about shells, and then we did the same thing for beams as well. Now we want to do the same thing with materials, because we have seen that for a long period of time there were fabrics, wood, so this is equivalent to your truss age, like in terms of the geometry, and later on metallic alloys. And the more modern and rapidly increasing percentage, both by weight as well as by in terms of the volumes, is the composites. And it's here that we are asking the exactly same questions, same set of questions of why, what, where, and how, what we did with the geometry earlier. We are posing exactly same questions as far as the composites are also concerned, right? So what we did in the previous class, towards the end of the last class, is to answer the first question here, why. So that is already done. So where we generally answered why we are using composites in spite of certain things, that is essentially it has certain disadvantages, which is why I titled even that video recording as why not 100% composites, because you see mostly it is like 50-55% of composites by structural weight and about 70-80% by structural volume. It's not yet 100%. You still use, for example, steel for the undercarriages, etc. So some of those disadvantages that we mentioned in the previous class are essentially coming up, which is the reason why we continue to use a mix and match policy, right? Same thing over here. You could have used either shells only, which is monocoque, or beams only, which is your truss. So remember that when you're talking about truss, it's actually those 1D structures alone, okay? Rod-like structures that you're talking, which are taking only the axial loads. So you're essentially seeing that either one of them, shells or beams alone, are not doing the job properly, and therefore you went to semi-monocoque, which involved both shells and beams, right? Same thing over here. In the case of the composites, you're seeing that composites by themselves are not doing the job, so you need to use them along with some metallic alloys as well for some of the components, or parts of some of the components, which is what we tend to do. Now we want to get to the next question. Now that the why is done, we want to get to the second question there, what. We did the same, all of those as part of your homework as far as the geometry is concerned, but now we want to do that in terms of the material, in particular the composite, right? So what are composites? So that's the question that we would like to answer next. Now if we want to answer what are composites very clearly, because you've already seen some examples of it, most of the composites that are used in aerospace engineering are fiber reinforced composites, which means they have a fiber and they have a matrix in which the fiber is impregnated or is essentially part of it, and therefore it's doing multiple functions. So if we want to understand that what a little more specifically, we have to go back to the why, not of the composite, but why of the components of the composite. So the composite is having two parts to it, the fiber and the matrix. So to each of these, I would like to ask the question why, then I would be able to understand what are composites. So to answer this question about the composite, I have to do a why for this, why fibers and why matrix, which is what most of today's class will be all about. Okay, so this is the question that we are trying to answer here. What is
slide this?
Sure. Is this fine?
Mm-hmm.
Okay, so as I said, we are trying to answer this question, what are composites now? And so let's probably get your answers. What do you think can be classified as a composite and what is not a composite? So how do you differentiate?
I think composites are generally like distinct. Like, they're like not necessarily homogeneous pictures, but like they're distinct two or more materials combined together.
Mm-hmm.
So as we mentioned with matrices,
Yeah.
there's different ways of creating composites where it can be like you embed small parts of one material into another material, or you can do long strips, or you can do even like layers.
Mhm. Okay. Yeah.
I
And
would say like two materials that have two different areas of expertise. That you can
good. Yeah. Absolutely. Absolutely.
use
Absolutely.
them both in tandem.
Fantastic. Yeah. Yeah. And this, both the answers Nafiz and Anai gave, what you're saying is essentially going back to the first story that we started off this course with, the hare and the tortoise. And you brought about a beautiful analogy there in civil engineering where you talked about the steel reinforced concrete. Okay, you talked about steel as the hare, if I remember right, and the concrete as the tortoise, right? So I would want you to revisit that homework once again in the next Monday. So use the same slides, just replace that civil engineering example with this aerospace engineering example, that is the fiber and the matrix of a composite, and just see most of it will remain, the storyline will remain the same, but try to see where the distinctions are. Okay, so I want to focus on both these aspects, the similarities and the distinctions between both of these are composites. Okay, and the steel reinforced concrete has been there for much longer compared to the kind of composites that we use today on aircraft, polymer matrix composites. And even before that is the bone and the wood that we have occurring in nature, both of which are composites as well. So composites, even though it might seem like it's a recent history as far as some of the engineering composites application is concerned, in terms of the concept, it's been there for a long period of time. So just so next Monday you can come back to me with the same set of slides, but make a few modifications to that to change your whatever you used as steel as fiber and the concrete as the matrix. Then we will see how things get modified. Okay. So next, even before we get to composites, we have to see, if not composites, what were being generally used as structural materials, right? So structural materials can broadly be classified into metals, by which we of course don't mean the pure metal, it's mostly the alloys that we are talking about. In ceramics, starting all the way from pots that people used to store food and liquids like water, etc., all the way to more and more refined versions of that for more rigorous structural applications. And the third category is polymers. So broadly, if you look at almost all these structural materials that have been used will come under one of these three categories. The composite is unique in that it can take either from different classes or within the class there are multiple, because each is a family. So like in metallic alloys, we already saw iron-based alloys like steel, titanium alloys, aluminum alloys. There are a bunch of other alloys as well. So you could take any two of them and mix and match, as I pointed out, to come up with something which can do better, like the other episodes of the hare and tortoise story, where you're seeing that teamwork happen in the fourth episode, and there essentially you're trying to bring in the advantages of both while working out the disadvantages or whatever are the issues with both, right? Now there is a possibility also to choose not only within a particular one of these three families two members, but across them, which is what, for example, is done in the case of some of your, let's say, the most commonly used what is the most commonly used fiber composite in aerospace engineering? Carbon epoxy, right? So carbon is which category, which of these three does it come under? Carbon?
Yeah, and epoxy is also a polymer.
Yeah, epoxy is a polymer, but carbon is more like a ceramic. Yeah. So because it's essentially the kind of characteristics it has, like brittleness, etc. So it goes with that. The polymer also, of course, once it is gone through a process of the autoclave and etc., it becomes a brittle thing. But brittle is not the only basis of classification for these kind of materials. So there are lots of other things, like for example, the polymer, by the very name you see, poly means many, and mers are monomers. So you have chains formed from these monomers, and typically they are usually in random orientation. But if you bring it in a particular geometry, you can kind of align them mostly in a particular direction to enhance the performances, etc. Okay, so you already see the most common example of CFRP, which is the abbreviation used for carbon fiber reinforced plastics. The plastic is essentially a polymer, an example, and the carbon is a ceramic. Okay. And we've been seeing some examples of boron aluminum, for example, boron aluminum composite, where the aluminum becomes the matrix, which is a metal, and boron is a ceramic, because boron fibers are nothing but carbon fibers which are coated with boron, as we already mentioned. So it becomes essentially a thicker or larger diameter carbon fibers with the boron properties essentially enhancing the stiffness or the Young's moduli of the material, right? So now we come to a fourth category, therefore, where we are essentially going to combine some of these either within one of the above three families or across the families. We just try to get two materials which are very different from each other, but the important thing is the compatibility that you're talking about. Okay, so as both Nafees and I hinted, it's essentially talking about two materials over there. So let's be a little more precise in that, and let's see, for example, even alloys are mixtures, right? So alloys consist of many different materials. For example, a titanium alloy could have aluminum and vanadium in smaller percentages going along with the titanium. So how do you distinguish, why don't you call a titanium alloy or any metallic alloy for that matter as a composite? What is the distinction between an alloy and a composite? The similarity is that both are mixtures, both have more than one component. So why not call alloys also as composites?
Alloys are mainly metal solutions, so I think on like an atomic level, they're more mixed than composites are.
Mm-hmm.
So they have like more of a consistent structure throughout. Composites are more heterogeneous.
Very good. Yeah. So you're getting to the most important point there when you said atomic, is essentially you're trying to look at the crystalline structure, which you're going to at a much lower length scale, that you're looking at how these are put together, right? Whereas in a fiber reinforced composite, for example, typical order of the diameter of most fibers will be of the order of 10 microns or so. So which is much more clear interface that you see between the fiber and the matrix, whereas you wouldn't see that unless you do some very high-end microstructure analysis. You'll not be able to actually look at the crystalline structures over there. This is much more evident. So it's more like thumb rule, where you're seeing that something that is much more distinct in terms of the interface. There's no chemical reaction taking place, but there is a stress transfer that is taking place between the components, in this case the fiber and the matrix, as opposed to in the alloy, where it is actually atoms of these different metals that are coming together. But remember always that it doesn't mean that if it is within the same family, it will always be the same, let's say an alloy. You could have two different metals, for example, which can be a composite. So you could have, let's say, for example, aluminum wires or aluminum fibers into, you can put into some other matrix, let's say a titanium matrix or whatever. Very common is polymer within polymer. Okay, so some of the composites that are used, for example, for some of your high-end carry bags, the suitcases that you typically use on flights, some of these are composites where you have a polymer fiber within a polymer matrix. So that's also a composite. Okay, so it's not necessary that they be across, like CFRP is across, right? GFRP or glass fiber reinforced plastic is also same, right? So glass and ceramics, carbon are ceramics, whereas the plastic is a polymer, right? But it need not always be spread across the families. It can be within the family as well. Okay, so polymer fiber within a polymer matrix, or a ceramic fiber within a ceramic matrix. And a very classic example for that is one of the highest end composites that we use in aerospace engineering today, especially for re-entry vehicles and the tiles which take the heat due to the re-entry, which is called as the carbon-carbon composite, right? So carbon-carbon composite, very clearly you see that the matrix is carbon, the fiber is also carbon over there because of the high temperature requirements over there, and also in terms of the structural requirements, also very large stiffness and strength are required. So that's an example where both the fiber and the matrix are in fact not only within the same family, in fact it's the same material. Okay, of course the processing is very different, the properties are slightly different because of the way in which the carbon matrix is processed as opposed to the carbon fiber, etc. But that is a very just like CFRP is kind of very, very critical for aircraft and helicopters, etc. Your carbon-carbon composite is very critical for your re-entry vehicles. So it's one of the things that is kind of unique to aerospace, because they are so expensive that they are rarely used in any other kind of applications, because such high temperatures also not very frequently encountered in other structural applications. Okay, so this is as far as some of the loud thinking that we do informally to get to this answer. So let's try to answer this in a little more formal sense. Obviously you should have a mixture, which means that more than one material that are there. So materials consisting of greater than or equal to, I should say, two chemically distinct constituents on a macro scale. Okay, so that's the important thing. We're talking about a scale over here, as opposed to what the alloys are at a much more smaller scale, as Nafis pointed out, more towards the atomic scale. So you're essentially looking at the crystalline geometry over there, and therefore the mixture is much more difficult to explore in terms of the constituents in the case of the alloy as opposed to in the case of the fiber composite. Okay. The other thing is adjective there is chemically distinct. That's again very important. So for example, you're talking about let's say glass and plastic, they're chemically distinct. But even here, where you're using the same material, carbon-carbon, the way each of those carbons have been processed, that is the carbon matrix and the carbon fiber, is very different from each other, and therefore there is in terms of the nature of that particular carbon, it's very, very different. As you know, carbon has a very wide range from amorphous carbon to crystalline carbon, all the way going up to graphite and diamond. So it has a range, and we are talking about a particular kind of carbon that is used for the fiber and different kind for the matrix. So essentially you might see in terms of the atomic nature, it might be the same. Sometimes the molecular nature might be the same, but exactly how those molecules are distributed, etc., there you could bring in a distinction. So more often than not, you have a chemically distinct set of constituents, at least two. Usually you will have more than two, or more than the fiber and the matrix alone, because you'll need certain additives depending upon certain other functionalities that are required of the material. The composite, you typically add a few additives. So since this is a very basic undergrad course, we will not go into the additives, because anyway they are very, very small percentage of the overall composite. We will focus on the two main constituents, which is the fiber and the matrix, which is what we will try to answer: why fiber and why matrix. Okay, so as I said, there are three categories of structural materials that have always been used historically, and even in nature for that matter: metals, polymers, and ceramics. And when you bring them together, either within the family or across the families, you members of the families, so you end up with a mixture which has distinct interfaces. In other words, very clearly you can see the interface, but it's not a weak interface which just gives up with a small load. So for your design loads and all the way up to whatever is the desired failure load, you would have to make sure that the interface is strong, because more often than not it is the fiber matrix debonding which is an issue. The fiber may not have failed, the matrix by itself may not have failed, delaminations may not have occurred between the layers, but between the fiber and the matrix, whatever is the bond, that might initiate an issue, and of course that eventually leads to matrix cracking if it is the load is large enough, fiber breakage and various other issues. So it becomes a little more complex as the damage grows. But the damage initiation to in many situations is because of the fiber matrix debonding that happens. Okay, and fiber reinforced composites, which is what we are talking about as the FR over here, whether it is GFRP or CFRP. The FR stands for fiber reinforced, and that's the most common kind of composite that is used in aerospace structures, at least, and to a large extent even a few other applications of composites. If you look at let's say some of the high-end automobiles, in fact some of the racing cars for F1 etc. are even more stringent in their requirements than some of the aerospace requirements, some of the regular passenger aircraft. So the material requirements there are much more stringent, and they also use some really high-end, high-performing fibers in the composite that they typically employ for many of these structures. Once again, if you're looking at sporting on the waters like yachts and things like that, then once again you would have really high-end materials that are typically used. So if that is the case, wherever you require high performance, whether it's in aerospace or sports, again sports not necessarily vehicles, even if you're looking at let's say a golf club, or let's say your tennis racket, or even a bicycle for sporting races and things like that. Many of these today are to a large extent made out of carbon fiber composites, right? So the first question we would like to ask is, before we get to the matrix about the fiber, why the fiber? Okay, so because it's the fiber, therefore we are talking about fiber reinforced plastics or fiber reinforced composites in general. So why this particular geometry of a fiber, which you know is nothing but you have a diameter which is smaller compared to the length, right? So that's what you typically call a fiber, right? But this pen also has a diameter which is small compared to the length of it. Do we call this a fiber? No. Why? Right, exactly. So this is more like a beam or a rod. What is the distinction between a beam and a rod on the one hand and a fiber on the other? This is analogous to something that we have discussed earlier as the distinction between a shell and a membrane. What is the distinction between a shell and a membrane? Right. So what you're saying is absolutely right, Nafis, that you're talking about one dimension being very small, one or two dimensions in this case, being very small compared to the third dimension, which is the length, right? So in the case of the shell and the membrane, it's the other way around. The thickness that you said is very small compared to the length and the breadth that you're talking about. So here also it is small, but it's not very small. Okay, so it's a question of degree of smallness. Okay, so you typically write something is less than, and you also write something is very much lesser than, right? So that's the essential distinction. So when you have a length which is very small compared to the breadth and the height, you end up with a beam which includes, of course, in our definition, a rod, column, torsional shaft, etc., right? Which can take shear loads, which can take essentially bending loads. Okay, whereas once you have the length very small compared to B and H, so it's the same thing on the left and the right. So once again we are comparing the length with the breadth and the height, but now we are talking about very small. What happens when it becomes very small? It's like one of the strands of our hair. Okay, so the diameter of the hair is very small compared to its length. So this symbol holds rather than this, right? So when you have something like that, so you see that it's very easy to bend our hair, right? So essentially you're talking about the bending stiffness going to almost zero, which is in the limit. So then you're talking about not a beam, rod, column, shaft, etc. Now you're talking about a fiber, right? So that's the essential distinction. And the same thing, instead of L over there, now I move the B also to the left hand side. So what do I do? Now I talk about L and B on the left hand side, and I have two categories. One is less than, the other is much less, greater than. Oh, here also I should have, I should have put this greater than. Greater than and much greater than, okay? So same thing over here when we are talking about so instead of taking one dimension to the left and the two dimensions to the right, you end up with what are called as 1D structures. Okay, here 2D because you brought two of the guys to the left. Now you're talking about once again greater than or much greater than the third element, which is just the height. Okay, h. So length and breadth are larger compared to height. Then you end up with what you call as shell, or if there is zero initial curvature, you call it a plate. Okay, here you could include even a frame for that matter. Okay, on the other hand, if it's much greater than, then it's the same issue that you had over here, where you talked about the bending stiffness going to almost zero, and therefore it became a fiber, right? Now here you're talking about this becoming a membrane. That's all there is to it, but you would see books after books, courses after courses for each of these individually, and it's necessary because the kind of amount of work that has been done over a long period of time by many engineers, scientists and mathematicians in order to get to the stage at which we are. But that stage at which we are, we don't need to bring in so much of a distinction between them and worry about that, because at the end of the day, all structures in reality, whether you're talking of beams or you're talking of plates, shells, membranes, whatever, they're all in reality 3D, right? But just that we got lucky from a structural analysis point of view. What we are doing is an analysis, or for that matter, if we are doing design, and you're talking of structural analysis or structural design, it's a fairly complex process because these structures have become so complicated, going from the truss-like to the monocoque, both of which were reasonably easy to handle. Now the semi-monocoque is a monster compared to those two, much more difficult to model and therefore to analyze or to design. So when you have something like that, we want to take advantage of this fact that something is much larger than, if you want to take advantage of that, instead of a 3D model, which is what reality is, of all structures. So we want to reduce minus 2D over here to get to 1D, and here we want to reduce by one dimension to go from 3D to 2D. So when you do that, obviously the number of degrees of freedom come down, and things become much more tractable, whether you're doing an analytical derivation or you're doing numerical solutions. Everything becomes much more tractable with the same kind of computational platforms if you're trying both, right? So that's the main direction in which we are going. Okay, so now it's very clear what is a fiber, right? So you know that the cross-sectional dimension has to be small compared to the length, but just being small is not enough. It has to be very small. So how small? Typically, for most engineering purposes, we have a thumb rule that we say that if it is 1/10 then it's reasonable. But at least if it's 1/100th or so, then it becomes much more accurate. In other words, when you're going from a 3D model, it's all if you have done it properly, it's always accurate. But if you're going for a 1D model, like what we see over here, then this 1D model, then there is a small drop in accuracy. Okay, but if you've done this this process, these two arrows are called as dimensional reduction, right? So if you have done this process correctly, which is beyond the scope of this particular course, but we will go to the final results, we will take the current state of the art without going into the derivations. But before we get there, if this process has been done properly, you started with a right 3D model, and then you've done the process correctly, then your 1D model can be as accurate as your 3D. Okay, so for all practical purposes, like the kind of plots that you have been showing, etc., if we plot the results from this model and this model, they will lie exactly on top of each other. Absolutely no difference with your bare eyes. Maybe if you want to do damage mechanics or trying to understand what is happening at the phenomenological level, etc., maybe a little more accuracy needs to be built up, but that can also be done with a 1D model, a little more refined kind of a 1D model. Okay, so that's essentially what we are looking at. Okay, so let's take a step back. I'm just trying to utilize this geometry of a fiber in order to introduce a certain concept which you're going to use pretty much for the rest of your course, okay, from the next week onwards. So if that is the case, the fiber geometry is very important because it's going to say a lot of things about how our beam geometry is. Just that this is a little more complicated compared to your fiber, because here you're having to deal with bending stiffnesses, okay, and bending stiffness in this direction, bending stiffness in this direction. As a combination, you can get the bending in any other direction, okay. Whereas with a fiber, I don't need to deal with bending because it has almost zero bending stiffness. So reason, once again, is the cross-sectional dimension very small compared to the length. Now these, whatever we have talked about over here, on the left I had the length, and here I had the length and the breadth. I can talk about this way if and only if I'm dealing with a statics problem. But you know that based on the loads that we saw for the aircraft, we saw that almost all the loads on an aircraft or any flying vehicle for that matter, or any transportation vehicle, are all dynamic. They vary with time, right? So if they vary with time, I can't talk about length, I should start talking about wavelength. Okay, we've touched upon this earlier. So if, for example, if this were to bend, let's just through one wave, then the first mode is dominant. Okay, so in other words, it's vibrating in such a way that this portion goes up, this portion goes down, or they keep alternating with time at a particular period, right? Whereas these 3 points that I'm touching right now are static, they're the nodes. Okay, so they don't move, whereas the rest of the things move, and the maximum movement happens here, the minimum movement happens here at a particular point in time, then they keep exchanging that, right? So that is one wave covering the entire beam length. So then I can still compare the length with respect to the breadth and the height. I have to check for this and see if this is true, then I can use a 1D model. But in most cases, it's not the first mode alone which dominates, maybe the second, third, fourth, etc. dominates, in which case, for example, I might have to consider only this much length. So in other words, 1/4 of the length or 1/6 of the length sometimes has to be compared with your breadth and the height, and only if that is 1/6 of the length is much larger compared to the breadth and the height, then it works. Which is why, coming back to our thumb rule, we talked about 1/10 or 1/100th. So 1/10 might work very well for statics problems or dynamics which involves only first mode of vibration, etc. When you go for higher modes of vibration, a 1/100th is a much better thing. So because if it's 1/100th, then even if you're going all the way up to the 10th mode, obviously you are having 1:10 kind of a ratio between your cross-sectional dimensions, which is the breadth and the height, compared to the length of this, or rather the wavelength, and then therefore you're still on the safer side. So this is a very, very important qualitative thing to keep in mind, because it essentially boils down to the applicability of the theory that you're going to get. However rigorous and appropriately you have derived the theory, and you have ensured that the starting point is good, it's appropriate, still you should know that there's a range of applicability of whatever model you develop. You cannot apply a particular model to beyond that range, then you could end up with completely erroneous results. So coming back to this slide, we are clear that it's fiber reinforced composites which are most common. So obviously there's something to do with the fiber geometry which is very critical. We also understood what is the definition of the fiber geometry, that the cross-sectional dimension is very, very small compared to either the length or the wavelength more specifically. And once we have understood that is the case, we know that therefore the bending stiffnesses are very, very small. Okay, so we don't need to worry about the bending stiffness. It's only the axial stiffness that we need to worry if it's a fiber alone. But then of course we put the fiber into the matrix eventually. But before we get there, we are trying to answer this particular question of what composites. So this is the what question that we are answering with respect to composites. And in the what question, what we are trying to deal with is why the fiber, right? So why the first important component of the composite, the fiber. So can you, now that you know what is a fiber, can you tell me why do you think the fibers have become so very popular in aerospace engineering or any high-end, high-performing kind of structural applications? What is so special about the fiber geometry? We know that the cross-sectional dimension is small compared to the length or wavelength. Therefore, it has very low bending stiffness. So what? Why should a fiber geometry be so helpful?
It's stronger compared to how small it is. It's like much stronger.
Absolutely, absolutely. So we really underestimate, for example, the strength of our hair strand. The amount of weight, if you do it appropriately, you can carry with just a few hair strands. It's enormous. Okay, so though it looks so flimsy that it bends so easily, in terms of taking an axial load, it is very, very good. Okay, so a very important point that and I brought out that fibers are strong. Anything else? Let's go back to what we were talking about in terms of the categories of design, right? We talked about the 3 S's. Remember, what are those 3 S's?
Strength, stability, and stiffness.
Very good, yeah. So we have those 3 requirements, right? So if we have those 3 requirements, what are the things which went into the numerator there? He already talked about sigma u. What else went into the numerator there? Yes, Young's modulus E, right? The stiffness. Because we are doing either a stiffness based design for statics in which E by rho is the material performance index, or if you're doing a dynamic design where you're trying to maximize the natural frequency, square root of E by rho is square root of the whole of E by rho factor is what we are trying to use as the material index. And it became even more density dependent when we went to the stability based design where we had E by rho cube, right? So we derived all those things, and so we are aware. So just like Anay pointed out that sigma u is very large for a fiber, the other quantity which Nafis pointed out, which is your Young's modulus, is also very large for a fiber. Okay, so these 2 quantities, of course, the density doesn't change so much. So the density, whether you are having the same material in a fiber form or any other form, the density remains reasonably close to, there might be a small difference, but it's mostly comparable. Okay, so what really changes is the absolute values of your tensile strength and your stiffness, which is the stiffness on the longitudinal direction in tension, which is what we are talking about, right? So that is the reason why the fiber is so very popular. So it has superior properties of the kind of properties that we are interested in a structural application. Okay, now let's talk about some examples of fiber materials to see, is it really true? What about the superior properties that we're talking about? Because remember, when we did the comparison chart, we were talking only about first only metals. We took just the 3 metals, which is steel, aluminum alloys and titanium alloys. And once we introduced composites, we talked about the combinations. We talked about graphite epoxy, boron aluminum. We talked about the carbon epoxy, glass epoxy, etc. So all of those were composites. Right now we are taking a step back, not talking of composites, we're talking of only fibers. Okay, because we want to answer why fibers, right? So let's look at the fiber properties. Obviously, these are much, much superior to the composite property even in a particular direction, which is tension, okay? So now, what are the typical fiber materials? We want to see some of the current state of the, not current, maybe about a decade ago. Now you might have even larger values for some of the cutting edge. So about a decade ago in terms of the commercial availability, because there are always some fibers which are still at the lab stage, they are still being developed, research stage, academics usually, and also sometimes you have developments which are taking place in research labs for defense, for the industry as well, if the industry is more visionary in nature, doing things for 10-20 years down the line, obviously they have to work on cutting edge materials. So many of those are not commercially available, but these are commercially available. For example, Toray is a company which makes a few fibers, and they typically give a particular name to each one of those fibers. So here we talk about two kinds of fibers. One is the M60J, the other is T1100S/G. And for these two, if you look at the properties, you see that the ultimate tensile strength is as large as 3.82 GPa. But what is more important for the M60J is the Young's modulus there, which is as large as 588 GPa. Okay? Whereas with the same carbon fiber, you can end up making something which is having an ultimate tensile strength of 7 GPa. As opposed to what you had here, 3.82 GPa. But when you try to increase the tensile strength, because of the way in which the fiber is manufactured, the kind of precursor that you start with, whether it is a pan-acrylonitrile like PAN or whatever. So depending on that and the kind of processes that it goes through eventually, very similar to like what we are talking about the alloys, right? So in the case of the alloys, we have depending upon not only the constituent of the alloy, what percentage of different elements are there in that alloy, but also the heat treatment and whether it is cold pressed and things like that. Depending upon those things, the properties can change quite drastically. Same thing over here. So both of these are examples of carbon fiber coming from the same manufacturer, but just because of the starting point and the way it is processed, you have in one case the Young's modulus is very large, so this is an example of a high stiffness fiber, whereas this in other case the tensile strength is very large, so this is an example of a high strength kind of a fiber. So just to give you an idea of the kind of values that are involved, much higher than the kind of properties that we are talking about for Young's modulus and tensile strength for the composite as a whole, because the matrix tends to bring that down depending upon the volume fractions that are there. So that will naturally bring it down. But nonetheless, this is the kind of values that we are talking about. Nowhere will any of the metals that we talked about, even steel for that matter, which was in absolute terms was the best compared to aluminum and titanium alloys, even that will not come anywhere close to what the values that we are talking about over here. So these are some of the typical, more than typical, I would say, higher end fiber materials for aerospace applications. But if you look at more commonly used ones, it may not be as high as E might not be as high as 588 GPa, but it's typically in the range of 6. The lowest that you see in this column is 65 all the way up to 385. So that range that you're talking about, at least in orders of magnitude, it is what we are talking about over here, right? So similarly, if you're looking at the ultimate tensile strength, so one of the cutting edge fibers is having about 7 GPa, whereas the highest you go here is about 3.5 GPa that you see over here, right? So now again, these are mentioned without any specific names. You see the same company Toray over here. Carbon fiber is manufactured by a few other companies, and that includes Hercules, for example. AS4 is very common, and also you have some of the other ones like within Hercules itself, there are other examples as well. Now, for a lot of engine applications, especially the containment structure, the silicon carbide fiber is becoming a very commonly used because of its higher temperature withstanding capabilities when used along with a titanium matrix. So titanium alloy which has some aluminum and vanadium content in it, So if you put into that the silicon carbide fibers, they are pretty good at high temperature capabilities as well as offering the strength and stiffness that are typically required in those kinds of applications. Here we're talking about containment structures, because there's an FAA requirement that when there is a blade out, if one of the blades of the let's say the compressor stage comes off, it should be contained within the engine. It should not come out of the body of the engine, because then it can hit any of the aerodynamic surfaces like the wing or the tail, which could be disastrous for the aircraft as a whole in terms of a crash. So you want to contain that. So you typically want to have something which is capable of high impact energy. So he works on impact problems as well. So the impact energy that needs to be absorbed is much more if you have, for example, a fiber like Kevlar amongst all the polymer fibers, because what is important there is the toughness, which is the area under your stress strain curve. Okay, so if you can have a much larger area under the stress strain curve, the energy per unit volume that you can essentially absorb even before your failure is pretty large, and once failure occurs, all the damage etc. takes in a little more energy, and essentially you're dealing with the impact resistance is much better. So either silicon carbide fiber in titanium or Kevlar fibers along with any kind of polymer matrix, which is an outer edge. And again, we're talking, remember, at the compressor stage where the temperatures have still not become very large. Once you go to the combustion chamber, the turbine and the nozzle, obviously even these are no longer satisfactory. You need to go to single crystal materials like nickel, etc., out of which some of those blades are made. And then you have to go for, if you're looking at high performance, then you go for metal matrix composites or carbon-carbon composites like used in re-entry vehicles and space applications. So those are all really cutting-edge research areas even today. A lot of labs both in the academia and the industry are working on many of those problems, right? Then just like carbon, you have many varieties. Within the Kevlar also you have two kinds which are very commonly used, but that is not the only two, but very most popular ones, Kevlar 29 and Kevlar 49. The Kevlar 29 has inferior stiffness, so in other words much more flexible, but in terms of the strength, the ultimate tensile strength, it's one and the same, and the densities are also one and the same. Okay, so typically you will see that the densities, for example, both glasses have almost comparable densities, whereas it is usually in the properties that there is a difference. And many cases even the Young's modulus will not, the strength will not change. Some cases the Young's modulus will not change, etc. So here you see, for example, both are changing in this. So E glass and S glass are two kinds of glass fibers which are mostly used for electrical applications, therefore E glass, and for structural applications, and therefore S glass. Okay, but once again there are many categories within them, etc. But you can see a small difference that is there. So you see the S glass both in terms of the Young's moduli as well as the strength, it is slightly superior compared to sigma u, and since the densities are comparable, what is important for us is the square root of E by rho or E by rho cube or sigma u by rho. All of those will be much better for S glass compared to E glass, but still not as good as for some of the carbon fibers. As I said, places where you have larger the stress strain curve, under that the area, which is the toughness that you're talking about, is more like, for example, it's a combination. There you cannot talk about the fiber alone over there, so you need to talk about the matrix as well, though sometimes fibers are used by themselves in the form of a net. For example, the containment structure that we talked about need not be a solid structure. It can just be like a matted structure with very close fibers to each other, so that it essentially catches things like a net. Okay, so if you go into some of the malls which have very large open areas in between, you would see certain nets. If somebody falls onto it, they will be caught on the net, right? So so that they don't go bang to the floor. So something like that. So essentially ability to take some impact energy, at the same time you want to ensure that in some cases like that example that I just told, you don't want the net to keep breaking every time, but at the same time in higher end applications like this, you want the energy to be absorbed from the impact, not only through deflections, even permanent deflections, but also beyond that damage and damages of all kinds, in order to eventually get to the overall whatever is the design value of the impact energy that you would like to absorb, right? Are there any questions on these properties and the comparisons these materials? Okay. So now there's much more qualitative difference that one brings out, more for economic reasons, depending upon whether certain fibers are much more affordable, like especially for industries like passenger cars, not talking about the high-end sporting cars, but the regular passenger cars, for example, or some of the other lower-end training goods, training sports goods, etc. Whereas the high-end sports goods and the high-end passenger cars, similar to aerospace, will be much expensive. So what makes something expensive is one, the raw material availability. So if it's not available in large quantities in the region that you are, and you need to import it, for example, from some other country, and its source itself is a smaller quantity, and also it depends not only the economics but also the geopolitics. Some countries will not be willing to share with certain other countries, etc. So all this has to be taken into account, and also because it's not just the need now, because this aircraft is going to last for some 20-30 years. You have to forecast and see how are the geopolitics going to be in that period. If I want to replace this structure, I have to replace with the same material. Will I be still able to get back that same material for maintenance, repair and overhaul, MRO? So when you want to do all those things, you have to bring these into consideration. So one thing that makes things expensive is the availability of the material itself, raw material. The second is the processing of that material, the processing costs. Sometimes the raw material might be available for a reasonable price, but in terms of the processing cost, that material might require much more stringent heat and temperature requirements. The autoclave settings might be such that for each cycle the cost might be a lot more, etc. So then you have to factor that in as well. So if you look at that kind of a factoring, very interestingly, it also breaks up into low performance and high performance fibers. Typically, most high performance fibers are expensive, more difficult to obtain. And if you look at the other end of the spectrum, you have less difficult to obtain, much cheaper fibers, which are also low performing. So instead of talking about in terms of money or the cost involved, because it involves too many factors and it's a developing field, we talk about it in terms of the performance, so that we have a metric to compare what is a low end fiber and a high end fiber. So instead of calling it a low end fiber, we call it a basic fiber, where the modulus is less than or equal to about 100 GPa. So you can see in this example itself, there are three over here, the E glass, S glass and the Kevlar 29. These are all having less than 100 GPa, and therefore they are called as the low modulus, or more in the layman's language as basic fibers. Okay, so and they are typically used extensively in situations where you have very high volume applications. Like for example, you don't manufacture that many aircraft. Even at the peak of the market boom, like it is currently in India, where we have thousands of aircraft ordered from both Boeing as well as Airbus. So it's a huge requirement. But even then, compared to the automobile market, for example, the volumes are not that large, right? So because the vehicles in automobiles sector might be manufactured in the order of hundreds of thousands of vehicles, so which means the requirement of material over there is much more overall, and therefore you look at those high volume applications, economics plays a much more stringent role over there. Yes, instead of using the basic fibers, if you use the high performance fibers, even in those applications, obviously their performance is going to increase quite a lot. The cars might be able to travel faster, it might be able to take a larger payload, it might last longer, in other words it's durable, etc. Manufacturing might improve, etc. The manufacturing processes, therefore the maintenance, repair and overhaul requirements might come down in terms of service requirements, etc. But is the industry willing to pay that extra amount, which again translates to, is the customer willing to pay that extra amount to buy that car? Because there's an initial cost for the customer and then there is a running cost for the customer. So when you make a car lighter, for example, the fuel consumption will be lesser. if keeping all other things the same, right? So if you have lesser fuel consumption over the life of the vehicle, you might be spending much lesser on fuel. But are the people in the market making the buyers, the prospective buyers, making that kind of a decision based on all those variables? That's what typically surveys take care of, to ensure that that is done, and then therefore they make decisions at the industry which material to go for. So more often than not, you will end up with basic fibers for wherever the applications are involving high volumes of production, and therefore economics is the lead requirement there. So there, yes, when there is crash worthiness requirements, like we already talked about the front portion of the cars in 150 years ago as compared to now, very rigid compared to very flexible. So there, if you want to go to higher end fibers, you might go for Kevlar 29, which is having a reasonably low E, but still compared to many others, it will have a larger toughness, and so you might go for that. But more often than not, it is usually the glass fibers. If it is a primary structure, you will go for S-glass. If it's a secondary structure, where load bearing is also one of its functions, it does something else which is its primary function, let's say a door for example, then you might even end up with E-glass if it's available much cheaper. So one example of the industry, as we already saw, is automotive, and the prime driver over there is the low cost that we are talking about. Okay. Now the other category, so it's just two categories that we are talking about, basic and advanced. So advanced fibers, obviously, if that is less than 100 GPa, this is greater than 100 GPa. That's what we are talking about. So we are not using strength as a criteria here, because rarely we reach the strength itself, because the design is such that certain margins of safety are built into it, etc. But the stiffness is something that is already kind of visible even at very, very small loads. Already every stress is going to cause a strain, and that stress strain relationship to start with for small strains is going to be a linear relationship, and that coefficient of linearity, proportionality is essentially your Young's modulus. So E plays a very, very critical role in terms of the deflections, and we already saw that it plays a very critical role for the dynamic natural frequencies. We also saw that it plays an important role for avoiding buckling, elastic stability based design, etc. So we see that E is an important criteria on the basis of which this is divided, and it so happens that economics also gets divided in the same way. One is affordable, the other is much, much more expensive. So examples, of course, are the carbon fibers and Kevlar. Of course, prices are coming down compared to carbon fibers a couple of decades ago. A similar performing carbon fiber today costs much lesser. But today we have much higher performing carbon fibers. So somebody who is doing a cutting edge design doesn't want to go for the fiber he couldn't afford 2 decades ago but can afford today. He wants to go for the cutting edge fiber today, which is very expensive. So that's the demarcation that you go there, both through economics as well as the interestingly, the word letter used for Young's modulus is also E, and so economics or E, essentially you're talking about that being the separating factor between them, and also exotic. So if you're looking at not just the transportation vehicles which serve important functionality, but also more like recreation, we're talking about sports applications, as we already discussed, the golf clubs, tennis rackets, bicycles, etc. All those things are typically made with the more advanced fiber reinforced composite, especially if it's at the level of performance like for the Olympics, etc. Okay, so what is the key there? You're talking about economics, you're talking about the structural performance. So essentially, there is, when you go from that category to this category, there is an increase in performance. How big is that increase in performance? Are the end customers, not just the intermediate industry, but the end customers, are they willing to pay that extra cost? So that is the basis on which this decision making process is typically done. Okay, we had a similar slide from the general internet in terms of steels. Remember the auto steels, we saw that what are the cutting edge all the way going from 20 to 200 GPa in terms of the performance over there. We also talked about the elongations over there going all the way up to 80%, etc. Now we want to do it for a big class of materials over here, where you have the tensile strength, which is one of the important criteria, which is the first criteria, in fact, of design. We talked about the strength-based criteria, and then the second, which is the reduce the deflections and or increase the natural frequencies, which is your stiffness-based criteria based on the Young's modulus. Okay, and both because typically, as we already saw, E has much larger values for most materials compared to sigma u, therefore in tension, and therefore we typically give the unit of gigapascal, which is 10 power 3 times what the unit that is typically used over here, megapascals, which is also can be put as Newton per millimeter squared, which is the typical unit used in most of the software like Abacus, ANSYS, Nastran, etc. Right? So keeping that in mind, so here is a chart. These are typical material selection charts, as we call. There are many such kinds of charts. You could even have a third dimension. We are bringing in density, or you could divide both by density already and plot specific values. So this is for other industries which are not weight critical, where they are not looking at light weighting. So then they need to look at just the absolute values. That's all that they need to look at, and that's what is the categorization over here. One of the pioneers who worked on this kind of charts is Ashby, ASHBY. He has a huge number of plots on various kinds of materials at his point in time, and so many of these plots are known by Ashby's plots for material selection, and researchers after him have also come up with adding more materials that have been accumulated over a period of time. So here you see all the way from the kind of materials that you talked about in your hair and tortoise story, the concrete, etc., all the way to some of the high performing materials like CFRP, where you see over there, we are looking at much larger strength, keeping the Young's modulus around the same. On the other hand, you can start from something which has a lower Young's modulus for a given kind of strength and keep going up in order to look at stiffer designs. So as we said, these criteria that we have, on the one hand you have sigma u dependent criteria, which is the strength based criteria, and we have for the other, we have the stiffness based criteria and the stability based criteria, both of which are going to depend upon your Young's modulus, right? How much it depends, of course, depends upon the final performance index that we derive. For the stiffness based design, both statics, for statics it is just E by rho. For dynamics, where you want to increase the natural frequency, it is square root of E by rho, and eventually for stability, to avoid buckling, we derived that it is E by rho cube. So all of them involve these two variables, E and rho, the Young's modulus and the density. So but here we are just looking at it from the absolute values point of view for a given density. So then we have all this classification that we see over here. Each of them is clustered. So this is the kind of clusters that I was talking to you about in your homework, for example, where you had points, right? So if you had different colored points, it would be like this green bunch of things, blue bunch of things, etc. It becomes a little more easier for you to explain what is the reason for that clustering and what is the reason for certain outliers, etc. Right? So at the end of the day, none of these are going to be the sole determining factors. Those three criteria that we derived, strength based, stiffness based and stability based, all three S's. So most of the time all three will be required. Okay, only in certain situations where you know for sure there is not going to be any compression at all, then you could probably deal with leave out the stability based criteria, because buckling is not going to be an issue there at all. But we saw in the first slide of the last class, we saw that even in the presence of pure shear, even in the presence of torsion, even in the presence of bending, either pure bending or due to concentrated force or distributed force, all these situations are leading to compression in some other direction at some other point. Okay, so because of that, if not the entire structure, at least part of the structure. Therefore, compression is an issue for pretty much all structures, and therefore even stability based design cannot be dropped out, and there we have a rho cubed in the denominator, making it extremely weight sensitive, and that's why so much of an importance is given for lightweighting aerospace structures. Okay, so As it is, we cannot directly use this. So if we want to really use this, we have to go for a different version of this where both of these are divided by density. And since each one of those materials have different densities as well, they will get redistributed and you will get different kinds of clusters over there. And those are also quite easily available today because a lot of aerospace industry decision makers need charts like this while making decisions on their materials and more specific decisions, because within CFRP, for example, it's broadly mentioned as CFRP epoxy over there, but there's as we saw, the Torre fibers, the Hercules fibers, and within Torre, the different categories, etc., can have a wide range. So that's where you see that none of these are points. You see, all of these are like ellipsoids, right? So what is it saying? What I told you about for the skin thickness, since you didn't have a single thickness of 0.02 but 0.02 to 0.04 inches. So I told you to have a line which extends there. Here you can't even have a line because it extends not in one direction but in the other direction as well. So now you have an ellipsoid for each one of those materials, which is what you see. Some have more variations because there are large number of categories of those materials. Some have less variation, so you have smaller ellipsoids. Some have circles because the percentage variation of both Young's modulus and the tensile strength are pretty much similar. So in many cases you see that these are horizontal ellipsoids, which means that rarely within a category of material there might not be too much of variation of Young's modulus. Similarly, density also doesn't vary too much within a category, but there can be a huge variation in the strengths because of the way the component is manufactured or what precursor you start the manufacturing process with. Okay, so there's maybe a few more things about this I will talk in the afternoon class, and then we'll move on to further emphasizing the answer for our question we started out with, why fibers. Thank you. If there are any questions, you can ask me now or in the afternoon class.
Can you clarify again what you want us to do for the homework?
Yeah. So you go back to the hare and the tortoise story. So you have already brought in the analogy that the tortoise is the concrete and the hare is the steel that is reinforcing it. So it's essentially a civil engineering application, right? But now since that day, because that homework was given on day one, when we had not done much of structural analysis from an aerospace perspective. Now we have understood a lot of things. We have understood that composites are the dominant material that is used. Fibers and matrices are there. So there is a certain purpose to them. Okay. So today afternoon as well as Wednesday and Thursday's classes, I will be talking a little more about these functionalities. Right. So now you will have an understanding. If I were to replace the hair from the steel fiber to the typical fibers that I used here, like carbon fiber or a glass fiber, and if I want to replace the the concrete with the matrix, which is polymer matrix over here, like epoxy. So then what things change, because now you have an idea of these properties. You have these design criteria that you're talking about, strength, stiffness. You have the stability based criteria as well. So don't go into the numerics of that. I want a more qualitative, exactly like the way you did it. So you don't have to change your slides too much, whatever you already presented. You just have to bring in this newer kind of materials. There will still be a lot of similarities, because at the end of the day, the reinforced concrete is also a composite, right? One of the first engineering composites humankind has used, right? After natural composites like wood and skin, etc., right? Bones. But then from there to now where we have moved a lot. We have made a huge strides in engineering progress, and therefore I want you to bring in those subtler aspects into picture. And it's a loud discussion as always. The homeworks when you present, I will try to interact with you and try, let's make it a learning process as well.
Yeah. So you want it to be like a different material, so it's a different epoxy.
Okay.
So do you want us also use an exact example or general?
I would go with a general, but if you see any advantages of using a specific example, that's fine with me. Okay.
So more specific than last time, basically.
Right. Not specific. It's still generic, but just the application is more specific, because instead of there we're talking about generally as a life skill, it's good to work in teams. It's good to be fast, not only fast but also steady, etc. So these kinds of things that were general lessons for us. Now we are trying to boil it down to more of the aerospace composite and see how it's much more relevant here.
This is the next one.
Yeah.
Like general radius and general flat.
Like
Yeah.
specific application.
Yeah.
Okay. So bon appetit.